All right, today we are diving deep, and I mean really deep inside the atom. We're going to meet two of the most powerful and honestly weirdest particles in the entire universe. These guys are the ultimate change artists. They're the reason matter itself can transform. So let's get into it. So let's start with a really fundamental puzzle. You've got a neutron and a proton. One's neutral, one's positive. They're supposed to be two totally different things, right? So how on earth can one of them just turn into the other one? It's like a subatomic identity crisis, and it happens constantly in things like radioactive decay. The answer, it turns out, lies with a force that doesn't get a lot of headline. And that culprit is the weak nuclear force. Now, it's not famous like gravity, and it's not as powerful as electromagnetism, but it has this one unique superpower that nothing else has. The weak force is the only force in nature that can change the flavor, or the type of a particle. It's the engine that drives transformation at the quantum level. But here's the thing about forces. They don't just happen. They need a messenger.
And this is where our main characters finally step onto the stage. See, every fundamental force has particles that carry it, that do the work. And for the weak force, its messengers are frankly some of the most fascinating and, as we're about to find out, heaviest particles in the whole Standard Model.
So let's meet them, the W and Z bosons. These are the particles that actually get the job done for the weak force. When a particle needs to change its identity, it calls on one of these bosons to mediate the whole deal. But, and this is important, the W and Z bosons have very, very different jobs. Let's break down their roles, because it's pretty cool. The W boson, think of it as the change artist. It carries an electric charge, and when it interacts with another particle, it can fundamentally change its type and its charge. This is the secret sauce behind that neutron to proton trick. Now, the Z boson is more like a momentum mover. It's neutral. It doesn't change a particle's identity, it just gives it a little nudge, transferring some energy and momentum. It's crucial for things like neutrinos scattering off of stuff. Okay, so let's actually watch the W boson do its thing. Back to our neutron, right? It's made of one up quark and two down quarks. During beta decay, one of those down quarks literally spits out a negatively charged W boson. And bam! Just like that, by throwing away that negative charge, the down quark flips into an up quark. All of a sudden, you've got two up quarks and one down. And that's no longer a neutron, it's a proton. The W boson has done its job, and then, poof, it's gone. It decays in a tiny fraction of a second. This all sounds pretty neat and tidy, right? But back when physicists were first figuring all this out, they hit a major wall, a huge problem, and it all boiled down to one single thing: mass. You see, the theories that worked so perfectly for electromagnetism, the force carried by the totally massless photon, well, those same beautiful theories predicted that the messengers of the weak force should also have zero mass. It was really the only way the math seemed to work out in these so-called gauge theories. But, and this is a huge but, there was a massive contradiction staring them in the face. We know from experiments that the weak force is incredibly short-ranged. Unlike electromagnetism that reaches across the cosmos, the weak force basically works only inside an atom. And in quantum physics, there's a simple rule. The heavier the messenger particle, the shorter the range of the force. So for the weak force to be so incredibly short-ranged, its messengers couldn't be massless. They had to be heavy. Very, very heavy. So, how heavy are we talking? Get this, about 80 times more massive than a proton. That is a mind-boggling number. These particles are absolute heavyweights, more massive than an entire iron atom. And this just completely flew in the face of the early theories. And that right there is the whole key. This is a great analogy for it. Their sheer weight is what limits the weak force's range. A massless photon can be a long-distance shouter, sending its message across the universe. But the massive W and Z bosons, they're close talkers. They're so heavy they can only carry their message a tiny, tiny distance before they just run out of energy and decay. So how do you solve a paradox like this? Well, it took one of the most brilliant ideas in all of physics, the Higgs mechanism. The idea was that the weak force and electromagnetism were once part of a single unified force, with a perfect symmetry that required all its messengers to be massless. But this symmetry was broken right after the Big Bang. The Higgs mechanism proposed this invisible field that fills all of space, and as the W and Z bosons move through it, they interact with it. They get bogged down, and that's what gives them their mass. It was an absolutely elegant idea that saved the whole theory. Okay, but a beautiful theory is just that, a theory. You've got to find the proof. You have to actually find these theoretical heavyweights. So the hunt was on. And the epicenter of that hunt was going to be CERN, the European Organization for Nuclear Research. So the theory drops in 68, and the race is on. The first little clue pops up in 73 from this wild experiment called Gargamel. It saw signs of the Z Bosons work, these neutral currents, but the real smoking gun, that took another 10 years. In 1983, using a particle accelerator powerful enough to actually create them, two experiments, UA1 and UA2, directly detected both the W and the Z boson. It was this incredible moment, a total confirmation of the theory. It was so huge, they got the Nobel Prize for it just 1 year later. That's fast. So you might think, okay, case closed, right? Discovery made, Nobel Prize won. But that's not how science works. The story is never really over. The search for a deeper understanding always continues, and sometimes it leads you to brand new puzzles. You see, knowing the W boson's mass down to the last decimal point is a huge deal. It's a critical number in the Standard Model, and if the real measurement is even a tiny bit off from what the theory predicts, that could be a crack in the wall, a hint of brand new physics beyond what we know. So scientists have been trying to nail down this number for decades. And just recently, this whole thing got really interesting. For years, all the measurements pretty much lined up with the Standard Model's prediction. But then, in 2022, a team at Fermilab announced a new measurement that was way heavier, a serious outlier. The whole physics community just went wild. Was this it? The first crack in the Standard Model? Well, not so fast. Other teams rechecked their data, ran new analyses, and in 2024, a new world average came out that pulled the value right back in line with the prediction. So does that mean the 2022 result was a mistake or a failure? Not at all. This is exactly how science is supposed to work. It's a perfect example of the scientific process. A surprising result comes out, it challenges everything, and that forces the entire community to double-check their work, re-examine their assumptions, and push their experiments to be even more precise. It's this beautiful, self-correcting process that always makes our understanding stronger. So at the end of the day, what's the one thing to remember? The W and Z bosons are the heavyweight champions of change in the quantum world. Their incredible mass is what makes the weak force so short-ranged, and their interactions are what allow matter to transform, powering the sun and making everything possible. I mean, think about it. We just talked about these tiny, fleeting messengers that can literally rewrite a particle's identity. It really makes you wonder, right? If that level of transformation is just a normal part of our universe, what other cosmic secrets are just sitting there, waiting to be uncovered in the quantum world?